Thank you, Leonardo. My name is Cristina Luna. I'm a robotics project manager from GMB. And today I'm going to present you the European rover system, a new initiative by ESA, with this talk designing a multipurpose rover for future lunar missions. Okay, I'm doing my best, I promise. One, so I think maybe, if not with the, well, by hand. Thank you. Great. The talk goes as follows. I'm going to introduce the project and then go into the rover with the baseline, the locomotion concept, and also the onboard software and autonomy part, and the test campaign. I would really like to also talk about the thermal analysis and energy budget, but only 10 minutes talk, so I will do my best. Okay. EMRS is a multi-mission project, which means that the rover needs to do many different things depending on the mission. In the beginning was targeted for 3 missions, now it's for 4 missions. The first ones are the Polar Explorer and the ISRU pilot plan. The Polar Explorer 1 is devoted to put the rover on the South Pole on the Moon, and dedicated to extract some water ice volatiles, and also to develop some geophysical science there. The South Pole, you know, there's a nice illumination conditions, also a good communication status, so it's perfect for lunar geological mission. Also, the ISRU plan is a complete different mission because the rover needs to carry almost 300 kilos of regolith, and to transport this regolith to the pilot plant, able to extract resources from them. The next missions are the Lunar Geological Exploration Mission and the HALO missions. The Lunar GEM is similar to the Polar Explorer in terms of the requirements, but it's targeted to 3 different scenarios on the near side of the Moon. The HALO, many talks on this conference about the mission, is targeted to mount a complete astrophysical observatory on the far side of the Moon. That means that the rover needs to be able to deploy antennas and to assemble the observatory. That means, of course, that the rover needs to carry a robotic arm, a robotic manipulator. In this case, we are designing the GMB Lunar 1. As you can see on the right picture, it's targeted also to put objects on the Moon and to assemble them, planetary assembly rover. Okay. The project team is a consortium led by GMB in Spain, with the collaboration of ABS from Spain, also with HDR from Greece, OHB and DLR from Germany, and GMB from UK also. Moving now to the rover, EMRS is a multi-mission rover that should be launched on the Argonaut. So it's one of the first Argonaut passengers. That means that we have a really constrained requirements of terms of space, because Argonaut has limited space for that. So it left on these dimensions, rover that on a stall position has a shape of almost 2 meters, on a deploy position 2.5 meters. You can see here also that we have this stove and deployed position, has different footprints. That's because we have designed a rover focusing on modularity. And in this case, the modularity for us is there's 3 different bays we have for payload. The central bay on yellow is devoted to the main payloads of the rover, the wheel controller, the thermal controller, and the common payloads for every mission. The side modules on green are devoted for other kind of payloads that need direct access to the surface. For example, a drill, or a spectrometer, the GPR, or any other scientific tool like that. On top, we have this this blue bay that is suitable for a mast or a robotic arm that is shown in the sample. This configuration, this design with the 3 different bays, allow us to configure the rover in many different ways. For example, you have here the ISRU configuration with the shovel, the drum, and the regolith container, and also the Polar Explorer one configuration with the drills or the spectrometers on the side. That's the thing for a rover for multi-purpose. It needs to be modular in this case. So the locomotion baseline is a 4-wheel rover with 4 independent suspension and steering. The wheels are wheels from configurable stiffness, or it can deflect depending on the interest. This leads in different locomotion modes that you can see on these pictures. The point turn that allows the rover to do a complete turn on the same spot. The crab turn is rotating with the parallel wheels, and also single and double Ackermann, and of course, apart the steering mode. We have this suspension that you can see is a spring with motors, because we are using a mixed suspension concept. It's a passive and active one that allow us to go on passive where you are traversing a flat surface and you don't need to put some strength on the suspension, and also allow us to do this walking mode, like moving one wheel and another it is legs, for example, to be able to overcome some obstacles, or also to increase the ground clearance, or to put the rover directly to the surface. Regarding the steering, maybe you have noticed that the steering motors are on the side of the wheel and not on top. Usually the rovers used to have the steering motors on top of the wheel. But in this case, after real effort on the design, we thought that it was a better idea to put the steering motors on the side, because it allows us to the space available on the Argonaut, and also to perform in a better way the operations of the rover. In terms of software and autonomy, this is the part of the wheel control and also the camera's control. We have selected for the breadboard and OBC based on the Siemens Korea KR260, which has a space grade sister, so it's really easy to develop something for Earth that can be directly migrated to space software. These things include all the winds controller, steering, thermal control, and every common payload controllers. But for having this multi-mission concept, we need a really high level of autonomy, E4 level for European standards. So we decided to reuse the software developed from CISRU and AIDE Ergo projects, the Peraspera ones, which means that we are having this level of autonomy with different models of perception or manipulation, multi-agent capabilities in case of, for example, the ISRU plan, that we could have many rovers in the same place, and also to be able to communicate with the control station to the moon base, other control parts. Regarding this perception component, we developed also this AI-powered software suite that enable us to perform this astronaut-robot collaboration for complex robot-robot on astronaut-robot scenarios. Because also in the 4th missions, it is not planned yet to have astronauts around. We really thought that in the meantime, there will be the rovers working with the astronauts alone. So we made a data set, as you can see on GMB spot on the left, high seas at Hawaii on the center, and also the ESA's planetary lab on the right, to be able to detect the the astronaut and rover interaction, and also the astronaut panels and other parts of the moon-based interaction. That's an example of it interaction. You can see is the astronauts and the robot on a maintenance mode. That also allows us to perform a safe navigation. We call it social navigation. It's the rover moving from, around the surface without putting in risk the astronauts and also the other robots' status. In terms of the test campaign, we developed this breadboard. You can see with the aluminum profiles. On the picture, we didn't test it with the side modules and top module because it was a locomotion test. But you can see it's the double Ackermann right now. And going deeper, these are pictures for the test campaign. We wanted to get some kind of goals in terms of traversing, excavation, and other locomotion and software tests. You can see on the top right picture that we were able to traverse up to 25 degrees of slope. The crack turn, point turn, and double Ackermann test, of course. On the bottom left corner, you have this uneven terrain traverse. You see the wheel is deflecting while passing the rock. Also the obstacle overcome, of course. And one of the most important things that we test at the alarms with the regolith simulant, that we indeed are able to excavate on the moon with this kind of concept. So let me finish with a question. Why to design one rover per mission when we can just design one to rule them all? Thank you.